Hello everyone, welcome to my presentation. So this is going to be my fourth presentation in this class, and this article is called Emergency Department Staffing: A Separated Continuous Linear Programming Approach. So to briefly explain this article, in recent years, the emergency department in many hospitals has experienced overcrowding, and it has affected the patients, healthcare workers, and hospitals. In this paper, it has been stated that the shortage of emergency department staff is considered to be a common factor to contribute to the emergency department overcrowding. And this paper presents a new model to address the emergency department staffing. The model is kind of an optimization model called separated continuous linear programming. By using the efficient algorithm, we can get the emergency department staffing level, which minimizes the total cost of the patients and the emergency department itself. So here is the organization of the study. I wanted to also add this to the presentation, so you will see the organization of the study. So first, in this article, they have defined the problem in the introduction. In the second part, the literature review on emergency department staffing has been done just to examine the different approaches, like linear approaches they have done before in the literature. And description of the emergency service process, the separated continuous linear programming model to minimize the total cost of patients, and summarization. So throughout this presentation, I will explain each of the steps. So in this section, I will mention what is this overcrowding problem leads to. We can actually consider this as a motive of the study as well. So when an emergency department has the overcrowding issue, it has been observed that the additional pain in these patients has led to unexpected deaths because they are not treated in time. Because of this overcrowding issue, healthcare workers have to overwork, and this affects their efficiency in work. Regarding this, the chances of medical errors and medical disputes are increasing. At the same time, emergency department crowding also affects the normal operation of the entire hospital, leading to a longer hospitalization time for the emergency patients. And this lowers the capability of the hospital to meet the needs for hospitalization of the non-urgent patients. So many problems lead to overcrowding, and one of them is a shortage of physicians to meet the fast-growing demand for emergency department. There are several reasons for the shortage of physicians, and one of them is the high operational costs of the emergency departments. Since the physicians' salaries represents a large part of the operational costs, this is a problem. There is not enough motivation for the hospital to improve their service by increasing the number of physicians. Obviously, improving the quality of emergency department staffing decision is just one approach. The management authority would like to know the least amount of physicians emergency department needs to provide improved quality of service so that the degree of emergency department crowding can be relieved to an acceptable level. So shortly, this paper provides a new approach to balance the waiting cost of the patients and the operational cost of the emergency departments. And the objective is to find an appropriate amount of physicians and their scheduling, which can meet the emergency department demand and the least total cost. So the most commonly used research methods for emergency department staffing is simulation, since it's a high complex system and simulation offers a natural framework to address this issue within. Simulation models often possess high validity because they track true system behavior fairly accurately. However, they yield fewer analytic inference than analytic models because they take input parameters and decisions as fixed. So a lot of experiments needs to be performed before an approximate optimal solution can be found. And the gap between the approximation of this optimal solution and the true optimal solution is unknown. On the other hand, although analytic models can never capture all characteristics of an actual emergency department process, stochastic models based on queuing theory are more appropriate for capturing the volatile and inherently non-deterministic emergency department reality, and they can be invaluable in providing managerial insights that improves the performance of emergency department process. So the purpose of this study is to introduce models for dynamic emergency department staffing without explicitly calculating the quantities of interest like patients waiting time, the fraction of patients who leave without being seen, and rather developing models direct towards using efficient algorithms to handle these quantities. And in this paper, the researchers have done this by looking at the emergency department system from a macroscopic perspective and use fluid network to approximate the overloaded emergency department system. So the paper actually had a segment to introduce the separated continuous linear programming, since it might be an unknown term for some of the readers. So the word separated refers to the fact that there are two kinds of constraints in this linear programming: the constraints involving integration and instantaneous constraints. Linear programming is one of the most successful mathematical models because of this wide range of industrial application, its speed and capacity in solving very large size problems. Linear programming has been pushed and extending to an ever-broadening frontier. So the emergency department process the treatment process in emergency department constitutes a multi-class stochastic queuing network with feedback. In this network, patients arrive at the emergency department randomly. The critically ill patients get to see the physician for the first time after triage. The treatment time for each patient is random, and there are several possible outcomes after a patient sees the physician, including maybe revisiting the physician after examination, or maybe going to testing and going to the emergency observation room, or just simply leaving the emergency department. So this is actually a figure to understand this and observe this treatment process better. In here, Server 1 represents physicians for treatment and Server 2 represents the physicians for examination and testing. The patients arriving at emergency department from outside are classified into N classes after triage based on patient's health conditions. The patients queuing before Server 1 and waiting for the first time to see the doctor are set in their first stage. After seeing the doctor, the patients either leave the system or enter their second stage, queuing before Server 2 and waiting for examination or testing. Upon getting their examination or testing results, the patients enter their third stage, which is queuing before Server 1 and waiting to see the doctor again, as we can observe from this figure. So I have mentioned the purpose and the approach of this model earlier. I will now talk about the mathematical model for emergency department staffing. So basically, by balancing the cost of patients and that of the emergency department, we would like to find an emergency department staffing level that copes with the time-varying demand for emergency department service, which can also balance the quality service requirement and the utilization of emergency department staff. So we address the emergency department staffing problems by two steps. In first step, we construct a queuing model to determine the appropriate scheduling policy for patients to minimize the waiting cost of patients given a specific emergency department staffing level. And in the second step, by varying the emergency department staffing level in separated continuous linear programming, we can find the least staffing level for emergency department, which minimizes the total cost of patients and the emergency department for the time interval. The patients who leave without being seen are ignored, and the emergency department system try hard to accommodate the patients who wait until seeing the physicians. In the emergency department process that we focus on, the arrival rate of the physicians and the service time of the patients are random variables. Instead of assuming that the arrival rate or the service time obeys some particular distributions, we only take the means of the arrival rates and the service time to describe this randomness. So here are some variables like in this model, and I would like to define them so when I show the models, it will be a little bit more clear. So the model is going to be attached, but briefly, the lambda I denotes the arrival rate of class I patients from outside at time t. Sj denotes the number of doctors or testing staff, as we have mentioned before, in server J. Bjt denotes the service capability of server J at time t for patients in the queues. Wij is the waiting cost of class I patients in their J stage. Cj denotes the service cost for each doctor or each testing staff in server J. And finally, Aij denotes the amount of class I patients in their J stage at time 0. So the objective is to minimize the cost for patients and the emergency department. So I will briefly explain each constraints. In the first one, we can obtain that the objective is to minimize the cost for patients and the emergency department. The first one denotes that the amount of class I patients in their first stage at time t is equal to the summation of the amount of class I patients in their first stage at time 0 and the amount of class I patients arrived from outside lessing the amount of class I patients serviced by server 1 and exit their first stage. The second one states that the amount of class I patients in their second stage at time t is equal to the summation of the amount of class I patients in their second stage at time 0 and the amount of class I patients who enter their second stage, lessing the amount of class I patients serviced by server 2. And the last one in here, there's going to be a couple more, states that the amount of class I patients in their third stage at time t is equal to the summation of the amount of class I patients in their third stage at time 0 and the amount of class I patients who enter their third stage, lessing the amount of class I patients serviced by server A and exit their third stage. It's a bit complicated, but this is just how the authors have stated it. So I have to quote from them. And these are these two sets of constraints are service capacity constraints. So I kind of separated them from each other. So the first one states that the total capacity consumed by the patients in their first and third stage cannot exceed the available capacity of server 1. And the other one states that the total capacity consumed by the patients in their second stage cannot exceed the available capacity of server 2. So, as we have mentioned before in the figure, these are for the service capacities. So here is the model 2. So basically, in the first step, we construct a fluid model, which was the model 1, to determine the optimal scheduling policy for patients in the emergency department to minimize the waiting cost of patients given a specific emergency department staffing level. Then, in the second step, we solve the model 2 to get the appropriate emergency department staffing level, which minimizes the total cost of patients and the emergency department. So here I will mention the conclusion that they have reached and the future work that they have seen some gaps in the study. So comparing with other existing approaches of on emergency department, this approach is more efficient to get the appropriate staffing level. Due to the results, the authors have stated that to determine the amount of emergency department physicians, if the cost functions are other type of functions, for example, convex and increasing function of the queue length is still unknown, and they have only considered how to determine the amount of emergency department physicians who are in charge of the patients arrived from outside. However, in reality, there is another decision to make, which is how to determine the amount of physicians who are in charge of the patients in the emergency room itself. So these are some gaps that they have seen in their study, and yeah, this is all that the article has covered. So thank you so much for listening, and I wish you a nice day.